Welcome. In this session in linear data analysis, we'll summarize the concept, methods, and evaluations that we used in this course. Under the concepts, if we were given some observations of variables and one of those variables was dependent on the other, then the method that we would turn to is linear regression. And linear regression is perhaps the best known and the classic method for linear data analysis. If all of our data were independent, what we turned to was principal components analysis, which is almost universally known as PCA. And PCA is a powerful way to cluster data, and it also lets us reduce the dimensionality of our data. When our data were at a sufficiently low dimension, what we would often try is we would try to find perform unsupervised learning, which is also called clustering of our data. If our data were of an appropriate dimension and we had labels for the data, then we would attempt to linearly separate. So linear separation of our data was our final main concept in this course. And I will observe that in the future, when you're doing nonlinear data analysis, what will often happen is the data will be transformed so that they become linearly separable. Under methods, what we had was our primary method was projection. And that is how we solved a large class of problems. Linear regression, it turned out, was projection. Principal components analysis is projection from a higher dimensional space to a lower dimensional space. And often linear separation was done by projecting data to a single variable and then finding a bias scalar. So projection, that was, let's say, especially to a one-dimensional vector space, which is why we began by looking at vector spaces in such detail. For clustering and labeled data, linearly separable data, the method that we preferred was we would partition the data. So partitioning data was a main method that we used. And partitioning, what we did was we divided the data into possibly non-equal but always non-empty subsets that ultimately contained all of the data. Underlying PCA in particular and many of the other methods was the singular value decomposition, which is also almost universally known by its acronym SVD. So the SVD was how we performed PCA, and it was also critical for us to understand how everything worked. A special case of this was the spectral decomposition. And the spectral decomposition was of a symmetric matrix. And this arose in many of our applications. And you do recall the spectral decomp, don't you?
Processing.
Right, give me the eigenvalue of that particle factoring in spectral decomp. That'll take a second.
When it came time to evaluate our data, one of the first methods that we used was cross-validation. And cross-validation comes in many guises, and the key observation of cross-validation is we didn't want to use just one method to evaluate our results. We wanted to use multiple methods and compare them, and cross-validation is one example of how to do that. Because we were dealing mainly with linear data, one of our other evaluations was we would find the mean and the variance of our data. And even when we were examining how well labeled data projected to a lower dimensional space or how well clustering performed, ultimately the index that we used was based on the means of data. When we had data that had labels, we would have the labels coming in, and then we would have classifications that we were producing from some algorithm. And to compare the labels and the classes, what we used was a contingency table. And contingency table is the formal term, and we also called that the confusion matrix. And the confusion matrix, if it's if we have a binary problem, that is, we have two labels in and two classes out, then the confusion matrix is 2 by 2. And we discovered that we could take that 2 by 2 matrix and we could map it to a single two-dimensional point. And that two-dimensional point was most often represented using false negative rates and false positive rates and true positive rates. And what we came up with was we had the receiver, operator, characteristic. And this is usually known by the acronym ROC, and when we have multiple confusion matrices or contingency tables, this becomes an ROC curve. And we were able to explore this ROC curve, and by doing that, we could better understand the performance of our classifier. Now, a little comment on my philosophy of teaching. What I've done throughout this course was I thought that I was my guide during your intellectual explorations. That is, the whole point of it was you. What I do as a guide is I point out prominent sites, and I'll tell you how I got to them and how you might get to those too. As you're doing your exploration, I do my best to try to listen to you as you observe your surroundings, because often you'll make observations that are novel to me, and I want to learn too. So I hope that my philosophy and these lectures have helped you to understand linear methods, and my very best wishes to you in your further explorations of data.